Alright, now as page 1 is uploading as a video, I'm moving on to page 2. Gas mixture at 27 degrees Celsius and 760 millimeters of mercury, so that's regular pressure, contains 1 gram each of helium, hydrogen, nitrogen, and carbon dioxide. How do their average molecular speeds compare? Now remember, Graham's law, the rate at which a particle moves is dependent on its molar mass, so that they all hit the sides with the same force. A larger molecules, or a larger atom or molecule, larger particle is going to be moving slower, and a smaller particle is going to be moving faster. So out of all of these, nitrogen's 28, carbon dioxide's 44, hydrogen's 2, and helium is 4. Carbon dioxide is going to be moving the slowest, then nitrogen, then helium, then hydrogen. They definitely would not be equal, and none of these other things would make sense like D does. So D is the answer. Let's move on to number 12. A mixture of 0.100 moles of nitrogen and 0.200 moles of oxygen is collected over water at an atmospheric pressure of 750 millimeters of mercury and a temperature of 22 degrees Celsius. That temperature is going to be important for the vapor pressure of water at 22 degrees Celsius. What that vapor pressure means, at any given temperature, when you're collecting a gas over water, some of that pressure is going to be due to water molecules evaporating into the gas that you've collected. So, what we need to know here is our atmospheric pressure, 750 millimeters of mercury. We have to factor out the water vapor pressure, which gives us 728 millimeters of mercury. That would be provided by nitrogen and oxygen in this case. Now, something I didn't really discuss a great deal is called mole fraction. I have a total number of moles of 0.100 plus 0.200. That's a total of 0.300 moles of gas. Out of that, 0.200 moles is oxygen. That means 2/3 of my total is oxygen, and 1/3 of my total is nitrogen. Therefore, 2/3 of my pressure is coming from oxygen. Remember, I have 0.3 moles total of gas. This is 2/3 of it, this is 1/3 of it. All gas particles act the same, therefore 2/3 of the pressure comes from oxygen and 1/3 of the pressure comes from nitrogen. So I take my 720 millimeters of mercury, which comes from the nitrogen and the oxygen combined, and then I need to divide that or multiply that by 2/3. So I have 728 times 2 divided by 3 equals 485 millimeters of mercury. Alright, next one, I might have to slide this up. Let me just check. Yes. Slide up a little more. Slide up a little bit more. A flask contains a mixture. Ooh, if I slide it up, I'll be able to fit everything else on here. There we go. Okay, so a flask contains a mixture of neon and argon. There are 0.250 moles of neon, which exerts a pressure of 205 millimeters of mercury. If the argon exerts a pressure of 422 millimeters of mercury, what mass of argon is in the flask? Okay, so this is, again, we're dealing with, well, actually in this particular case we're dealing with pressure and moles. Now if I'm deciding that 0.250 moles of neon exerts 0.205 millimeters of mercury, I can actually set up a nice cross multiplication to find out how many moles of argon would be in there, and then from there I can go from moles to grams. So if I have 0.250 moles and that exerts 205 millimeters of mercury, then I would get, and again, this pressure, because of this mole volume, is based on the volume and the temperature, which are assumed to remain constant. But what pressure I get is directly related to the number of moles of each gas. It's kind of related to Avogadro's law, although that's volume over number of moles. This is pressure according to the number of moles, but it's the same basic idea. So I don't know the number of moles of argon, and the pressure I get is 492 millimeters of mercury. This is like our stoichiometry cross multiplications. We just have moles on the top, we have pressure units on the bottom. As long as we keep our units consistent, we should get a nice number. So I do 205, no, not another pen still going. Alright, I will have to switch to another. I'll use a pen, unless I can find another pencil somewhere. Ooh, I got a whole pack of pencils here. Alright, red pen now. So I have 205 x equals 0.250 times 492 divide by 205 divide by 205. I end up getting, this will give me, remember, the number of moles of argon set up in my cross multiplication. So 0.250 times 492 divided by 205 equals 0.6 moles of argon. Oh, come on. And again, the understanding here is that any mole of a gas exerts the same pressure under the same conditions. So X equals 0.6 moles of argon. I go over to my periodic table and I find out that argon, its molar mass is 39.9. Therefore my mole units, my moles cancel out. So 0.6 times 39.9 equals 23.94, which is very close to 24 grams of argon. Alright, let me see if I'm still able to fit. Yes, I am. A gas in a closed, flexible container is slowly cooled from 50 degrees Celsius to 25 degrees Celsius. What is the ratio of the final volume of the gas to its initial volume? Assume ideal behavior. Now, I'm not given a value for the volume, but I can assume a value for the volume. And a good value to assume is 1. So if I have a volume and I have a temperature, I'll set my V1 to 1.0 liters. My T1 would be 50 degrees Celsius. Oh, come on. Which would have to be converted into Kelvin to become 323 K. And then my V2, I don't know, and my T2 is 298, so I'm cooling it down. I shouldn't expect a tremendous difference. What I'm going to do is solve for V2 and then find the relationship to V1. So it is 1 over 323 equals V2 over 298. So I have 323 V2 equals 298 divided by 323 divided by 323. My V2, again, it should be smaller. My temperature went down. So if the temperature goes down, the volume goes down. And now I have 298 divided by 323, which is 0.92206, and I'm going to lose this pencil too. So that equals, I should just use pens. That's all. Okay. 0.9226. So the relationship is 0.923 to 1. That's the letter C answer there. Get all of this broken lead out of here. All right. A 2-liter balloon at 20 degrees Celsius and 745 millimeters of mercury floats to an altitude where its temperature is 10 degrees Celsius and the air pressure is 700 millimeters of mercury. What is the new volume of the balloon? This has a volume, it has a temperature, it has a pressure. We have the combined gas law to handle this because there's no mention of a number of moles. And again, since I'm not using the ideal gas constant, I don't have to convert my pressure units into any, another pencil's dead. I don't have to convert them into kilopascals if I don't want to. Could I do it and get the same answer? Sure, but that's a lot of extra steps. What I always must do, however, is change my temperature to Kelvin. So I have my pressure. Initial pressure is 745 millimeters of mercury. My initial volume is 2. And my initial temperature is 20 degrees Celsius. Add 273 to get Kelvin. I get 293. Equals now, pressure is 700. Excuse me, V2, I don't know. And my T2, it's dropped to 10 degrees Celsius, which is 283 Kelvin. All right, now I have to solve for this. I do, well, let me just put my numbers out. So, just to clear this up a little bit. 745 times 2 equals 1,490 divided by 293. 745 times 2 divided by 293 is 5.085 equals, and now I have, so multiply both sides by 283. I end up getting 1,439. Am I still on the screen here? Yes. 1,439 equals 700. V2 divided by 700 divided by 700, and I get 1439 divided by, so my volume has gone up a small amount, but not a tremendous amount. Again, the pressure didn't drop that much, the temperature didn't drop that. I'm sorry, the pressure went down, temperature dropped, so they kind of counterbalance each other actually now that I think of it. So my V2 is 2.056, or V2 equals 2.06 liters. Answer is C. All right, let me try flipping this paper. And let me take a look here. Move it down a bit. Move it down a bit more. And I should be able to fit the first 3 problems. This takes us through most of the practice test. I will also have the practice problems, the review problems. I will make a video for that, but I think I will include this page 2 on one video. So, a gas diffuses 1/3 as fast as O2 at 100 degrees Celsius. This gas could be, again, the 100 degrees Celsius is just to establish that they both have the same kinetic energy because the temperature is consistent. Now, we need a gas that will follow Graham's law in this particular case. So 1/3 is fast. So 0.333 is the speed of this particular gas. and it's, oh boy, having another problem with another pencil here. This is why you don't buy pencils at the dollar store. Alright, so 0.333 is the rate of gas, we'll call this gas A, over oxygen. Oxygen would be 1 in this particular case. So that means it is equal to the square root of the molar mass of oxygen over molar mass of gas unknown. We'll call it gas U. And now molar mass of oxygen is now, so 0.333 equals the square root of oxygen, which is 32. That's the molar mass of oxygen gas over X. Now I'm going to square both sides, and I get 0.333 times 0.333 equals 0.111, we'll call it, equals 32 over X. So now I get 0.111x equals 32 because I've multiplied both sides by x so that my x on the bottom cancels out. Divide by 0.111, divide by 0.111. Now keep in mind, I'm expecting a gas that's much larger than oxygen. I will get a gas that is much larger than oxygen. Why do I expect to be larger than oxygen? Because it diffuses more slowly than oxygen. So then I get 32 divided by 0.011, oh boy, no, 32 divided by 0.111 is 288 grams per mole. Now looking at my possible gases, helium is 4, definitely can't be helium. This is 12, 24, 24 plus 5 is 27, 27 plus 19 is 46, far too small. 7 times 12 is 84 plus another 12, still far too small. Now this is 60, and then so 12 times fluorine's atomic mass is 19. That gets me to 228. 228 now plus 5 times 12, which is 60, gets us to 288, and that's our answer. So this, if I actually looked at it, just so you know, that's a pentane, and instead of the hydrogens being around the pentane, everyone is occupied by a fluorine. Moist air is less dense than dry air at the same temperature and barometric pressure. Which is the best explanation for this observation? Again, this is not a calculation problem, it's just a thinking sort of a problem. So, humid air, which is air that contains water, is less dense than dry air. So remember, at a certain temperature and pressure, you have the same number of molecules of a gas, regardless of the type of gas. If I have a chunk of air that has some water molecules in it, I'm going to have exactly the same number of particles as if I had dry air. Now, I didn't actually count my particles here, but in this case, I have the same number of particles as in this case. If the pressure here is, let's just say this is called wet air, humid air, and this is dry air. Wet air, some of those gas molecules are water, which has a molar mass of 18 grams per mole. In this one, I don't have water. All I have is the nitrogen, which is 28 grams per mole, and the oxygen, which is 32 grams per mole. Water has a lower molar mass. Water vapor has a lower molar mass. So anytime I have water molecules in there, even if I have the nitrogen and oxygen, I have lower numbers of nitrogen and oxygens because the water is taking up some of this space also. Therefore, because water has a lower molar mass than the other particles, you're going to have a lower density. So what would the explanation be? What H2O is a polar molecule? No, water in this case is a vapor, so it's bouncing around without any attractions like any of the others. H2O has a higher boiling point. That is true, but that has no bearing on the density of the air. H2O has a lower molar mass than nitrogen or oxygen. Nitrogen is 28, oxygen is 32, and water is 18. So if you're making a mixture that has a molecule with a lower mass, it's going to lower your overall density. And then water has a higher heat capacity. Well, that's probably true, but again, that's not relevant to this particular situation. All right, let me see how much space I have to fit 18. That's the last one I can do currently. A sample of gas occupies a volume of 9.23 liters and 345 K and 1.40 atmospheres. What is its volume at 525 K and 3.20 atmospheres? This is another ideal gas law problem. P1 is 1.4 atmospheres. V1 is 9.23 liters. And T1, this one's very nice, they actually give you it in Kelvin, 345 equals P2, which is 3.20. V2 is what we're trying to find, and 525 K. So pressure is going up. If pressure goes up, volume's going to go down. But at the same time, temperature's going up. So we will have to see what that does to the overall volume. Is pressure going to be a greater factor, or is temperature going to be a greater factor? So I do my mathematics really quickly. I do 1.4, and again, since this is a combined gas law, as long as I'm keeping my units consistent, I'm fine. There is no ideal gas constant. I do not need to change atmospheres to kilopascals. Here I can just use atmospheres. Could I change atmospheres to kilopascals and plug these numbers in and get exactly the same answer? Yes. But is that extra work? Sure, also true. So 1.4 times 9.23 divided by 345 equals 0.0374 equals, and then it's 3.20 V2 over 525. So I multiply both sides by 525. I get 19.66. V2, and I divide by 3.20, divide by 3.20, and I get my V2 value is 6.14. Part of this is I'm pushing down too hard, but part of it is this lead is really crappy also. All right. Come on. All right. So 6.14 liters. What does that mean? It means that that increase in pressure overwhelmed the increase in temperature, and I squeezed down my gas into a smaller volume. All right, 2 more problems. I'll see if I can fit both of these. Oh, look at that. I have a repeat. I wasn't even expecting that. Well, looks like you got off easy, because that's 6.14 liters. Also, I'll make sure I don't do that on the test. But, hey, you got a break there. All right. A 3-liter sample of helium gas is stored in a rigid, sealed container at 25 degrees Celsius and 1 atmosphere of pressure. The temperature is increased to 125 degrees Celsius. What is the new pressure of the gas? So think and look. 3-liter sample. Rigid sealed container, meaning the volume will not change. I have a temperature, I have a pressure. I'm increasing the temperature. I need to find a new pressure. That is a Guy-Lussac's law problem. P1 over T1 equals P2 over T2. I do not need to worry about the volume because it's in a rigid sealed container. So that volume is not going to change. The only thing I do need to worry about, again, I can keep atmospheres. I'm going to get my pressure in atmospheres. It looks like that's fine. I will need to change temperature to Kelvin. So my P1 is 1 atmosphere. My T1 is now 25 plus 273, which is 298. And then my P2 is what I'm trying to find. And my T2 is 100 degrees warmer, so 398. Now, 298, I can cross multiply here. 298 P2 equals 398 divided by 298 divided by 298, and I end up getting P2 equals 398 divided by 298 equals 7.48. What the heck? Something went wrong. No, actually nothing went wrong. That just seems like an awfully high. It's not on there. That's what the problem is. Okay. 1 atmosphere. 298. P2, 398. So 398 divided by 298 equals, yeah, okay. So I get 398 divided by 298, which equals, whoa, something went wrong. 398 divided by 398 divided by 298, it should give me a number not too far off the original pressure, but that is actually one of our answers. So number 20, P2 is 1.33 atmospheres. All right, that completes both sides of the part 2, page 2 of the gas law test, and I will review the other answers on a separate piece of paper. Again, I apologize for repeating myself. I don't even know how that happened, short of the fact that I was making this late at night. I won't do that on the test. I promise that. All right, I will double check everything because I'm making it over the weekend when I'll have more time and more sleep. So, last one was something different, and we will move on from there.